Okay, so Quant, you fairly recently launched your first commercial product, and I think it's a photonics-based native processing unit or NPU. It'd just be good to start with to understand, the background as to how you've reached, what's obviously an exciting milestone for the company.
Yeah, that's indeed it was. And I think to best explain how we came to this, it's really interesting looking back to the start of Quant. We started in 2018, and ever since we've been convinced about that photonic integrated circuits, especially based on thin film lithium niobate, can make a substantial difference when it comes to data processing. In the meanwhile, on this thin film lithium niobate technology, we control the entire value chain from building the raw wafers down to really having our own pilot line operating. Why this is because we are convinced that this material, among all the current discussed materials for photonic integrated circuit, is outstanding, especially when it comes to photonic computation. In contrast to other photonic material, it allows us, for instance, to change or manipulate the state of light at gigahertz rates without using electricity on the fundamental photonic circuit. This might sound very, very technical indeed, but this absence of electricity on the photonics layer allows us to control the light extremely fast, as said, in the gigahertz range, and more precisely than other materials can do. Because there is no heat on the photonic circuit. There is no heat spread. You can control the light very precisely. And openly speaking, initially when we thought about how to use this type of material, we were thinking about building quantum computers. We did so till 2022, and then we realized that there is a way faster way to a commercial product by building a photonic coprocessor without using photonic effects, but just the analog nature of light. What we understood back then was exactly this feature of purely controlling the analog fashion of light with this lithium niobate technology allows us to realize an analog computer for the first time with a precision of 8-bit. And this is basically the breakthrough. This is what we've realized with our product launch in November. And by that, we, so to say, let a dream come true, an analog computer with a precision that's meaningful enough to carry out computations that can compete with the CMOS world.
Okay, and you may well have partly been describing it there, but and if you have, perhaps you can just expand on it. But I know that the sort of core of what you're doing is the light empowered native arithmetics, or Lena, Lena, the compute architecture. So if you can either expand on what you've already told us, or explain what how that works in particular, that would be great.
So yeah, absolutely. So and to explain, so Lena is the complete compute architecture. It's more than just the light core, because our goal ever since was, if we bring such a new technology to a very traditional and existing ecosystem like the compute ecosystem, it has to be minimal invasive. It's a new animal in the zoo, but it shouldn't be so abnormal that no one wants to adopt to this new animal. Even if it's faster or better, it has to be natively to be integrated into this ecosystem. And this was always the narrative to compute this. So we basically wanted to bring it on the standard interfaces of the compute industry, PCI Express in our case, to the main board, on the main board level. And on the same side, we didn't want that the software architects have to change their source code. So in that sense, we also developed a low-level software stack to it so that it's natively compatible with the existing front layer software tools like PyTorch, TensorFlow, Keras, and so on. And you can see this by the products which we are offering. So on the one side, we have this PCI Express card, but what customers much more appreciate currently is our native processing server unit, which already has an x86 compatible mainboard on it. And it's pluggable via Ethernet into an existing rack system. And this is what we in total then mean by Lena. Lena is the photonic layer the hardware addressing layer and the low-level software stack.
Okay, and you referenced, I think, maybe not on that answer, the previous one, conventional CMOS technology. So I get it would just be good to understand, compare and contrast, if you like, what you're doing compared to conventional CMOS technology. And in doing so, I guess just bring out the benefits of what you're doing. And I guess as well, this particular applications which you think are a sweet spot for Quant.
Oh yeah. So if you just think about the technology, you can consider it as an analog computer. That's what it is at the heart. And it's an analog which is realized with light. So, and that's the main difference compared to conventional CMOS processors. So in contrast to the CMOS world, we do not have to translate mathematical functions into 0 and 1s or in transistor flips. We can natively execute the mathematical functions in an analog way. And this is where the leading performance and energy advantage comes from. So just a few examples that one get an impression how powerful this is. If you go on the fundamental mathematical level and you think about how many transistors would I need to carry out a summation, it's around about 200 transistors. Extracting a root is already 7,000. If you want to compile a Fourier transform, it's more than 1 million transistors. So the more complex the mathematical equation gets, the more transistors you have to use. On an analog circuit, you can essentially use one optical or analog element to carry out on such mathematical operations. But I also want to draw an honest picture here. I consider it as a co-processor to the existing ecosystem with a strong focus on complex mathematical equations as they, for instance, are needed for AI training. It is, like all other processors, not the egg-laying, milk-bearing jack of all trades. We have to understand that each processor has its distinct advantages, may it be a CPU, a GPU, or an NPU in our case, or in the future, maybe even a quantum, a QPU. And we need to consider this as a whole chiplet ecosystem to further propel computational performances.
Okay, and you mentioned there the obviously performance is perhaps the main driving force, but also energy efficiency is important. So I'm just wondering, sustainability. Everyone's aware of what's going on in the data center, the pressures there, the power consumption. So was that an important part of your focus as well to ensure that PICs obviously have a major energy efficiency advantage? Was that part of the attraction of doing what you've done? Certainly compared to, say, GPUs, the power consumption that those need.
Yeah, so this was the main reason why we were focusing on this new type of processors back then in 2022. Because what you back then already could see is that the possibilities of AI seem to be nearly endless. But currently, we ignore, and this becomes more and more evident, we ignore the consequences. I mean, the most obvious one is that the data center operators are discussing to put mini and nuclear power plants aside to rescue their energy, right? And if you look on a more fundamental level, one GPU takes 1.2 kilowatt. This is one oven in your kitchen. Now, a GPU server takes 14 kilowatt. These are 14 ovens equivalent in one rack system. And the whole rack system in total has more than 100 kilowatt in the meanwhile. So, I mean, from a sustainability point of view, it's insane, but it's also a nightmare when it comes to operational expenses, because there is clearly a lot of electricity fed into the system. When we then, let me explain this. So when you now remove all the sugar from the current hype on GPUs and the CMOS world, what we are going to notice that CMOS is still following the well-known scaling laws. It's computational density. It's the number of transistors per chip area that are the main drivers for performance and energy improvements. And what we currently see is that companies are making the chips larger, but not inherently better. And so there is not really a fundamental improvement on the chip layer. The next considerable improvement, what we can see is most likely when we're switching to the next node, to the 3 nanometer node on a productive level, which shall take place this year. I'm not in this industry, but this is where we see a next performance jump of this CMOS technology. On the other hand, if you change to the photonic core, you change the game, because you now open the door to an analog compute system. So for the first time, you can natively compute mathematical equations without the necessity of relying on translating them into bits and flops. And this advantage on its own is the true performance booster. And this can lead to the fact that you can drive the computational density, especially on complex mathematical equations like the Fourier transform, above the CMOS chip technology. And this is on the performance side, the justification. There is a second one, because light on the chip level is just propagating. Frankly speaking, it's not getting tired. Once you inject it into the chip, it's propagating from A to B without the necessity for additional energy. And then there is a third argument why this technology has advantages compared to CMOS technology. And this is due to the laws of physics, funny enough. I mean, the components of a photonic circuit, they're comparatively large, because otherwise you can't guide the light. They're on the orders of a few microns. Now, people might think, okay, the regular scaling laws of CMOS are not accounting to photonics. That's true. The photonic scaling laws come for getting ever more complex functions on a single optical device. However, our chips can be manufactured on semiconductor technologies from the 90s. So we ourselves currently using a 90 nanometer node technology in order to fabricate our photonic chips. So in comparison to the 3-5 nanometer foundry systems, which we are seeing in the world, this is a great advantage, because we can also repurpose outdated foundries to serve a new technology.
Yeah, and in all you mentioned, I think there about the performance, and I think you've carried out various tests to demonstrate, the impact of your solution when it comes to calculation requirements, I think particularly for machine learning applications. So perhaps you can just share what it is you've tested and the results, just so people can understand, how impressive, if you like, the technology you've developed is.
Yeah, so you're absolutely right. So we currently investigate this new technology in the context of AI, and the first demonstration was for AI inference. For an AI inference, we can showcase that this technology can bring up to 30 times power consumption reduction on the same equivalent computation than in comparison to a graphic card. Okay, that's fundamental, that's great. But for me, this is a closed use case, right? AI inference is, mathematically speaking, not too complex. You do and do over and over the same mathematical things. The true potential and the dreams come when we combine this technology for AI training. And to give you one example, for me as a mathematician, I'm looking to this AI training. You have tons of digital data points, and you try to fit your mathematical function to this set of data. And in the end, you have, let's say, 1 or 2 master equations, and you basically execute them and you get an answer. Now, we know from math that the linear approaches as they're currently used, linear functions as they're currently used with the GPU technology, that they're limited. You use them because these linear functions are nicely executable on the CMOS world. But if you switch to complex nonlinear functions, you can accelerate the training tremendously. And this is what we showcased on the first example. So what we did is, to the experts of AI, instead of increasing the parameters or the network depth in order to train on a picture, we replaced the transfer function. We replace the transfer function for a nonlinear equation, which is nicely to be executed on an NPU system, but rather complicated to be executed on a GPU. And by this, we can showcase that this system can save on this particular use case up to 50 times of parameters in order to come to the same training result. So this gives an imagination, and please, I'm always the person on the one side, yes, excited about the technology. On the other side, also wants to be honest. It doesn't account for all cases. It's a case dependent. Acceleration. If the problem is rather simple, the benefits of this technology are not so tremendous. But the more complex and the less defined the problem becomes, you're going to benefit from this additional mathematical complexity, which is easily to be executed on an analog or an NPU system of us.
Okay, and I'm wondering as well, I mean, I think you launched this back in November, so we're maybe a couple of months on.
Yeah.
Presumably before you launched it, you were already talking to partners, etc. But just be good to understand what the feedback has been, what, as I say, what partners are telling you. Where are you at from having made this announcement, I suppose, is the question.
So yeah, we were a bit we didn't expect such a tremendous response, positive response when we launched it during the Atlanta Supercompute trade show in November. Since then, we have we've collected a significant number of order intakes on the first system, which is great. All of the customers don't want to miss out on the chance to already get a hand on this technology. But for me, especially the second part is of a higher value. Yes, we are generating revenue with the first systems. That's great. But people are starting to think in this new direction. They're starting to considering this technology as part of the ecosystem. They're thinking about, or they're challenging themselves, is the CMOS world the right processor in order to execute on my problem? And this is how you, in the end, or to me, how such a product can start a paradigm shift, because for me, it's not just a product or an upgrade to the existing landscape. It's really a redefinition on a subset of equations, how you can efficiently and high performancely calculate on these problems. And I mean, the result, if we bring it into the ecosystem, if it's adopted, then we have a very good chance that we, from an energy perspective, can reach levels that are never going to be reached with the CMOS world. And in terms of speed, I would say, let's see. I mean, we're just standing at the beginning and understanding from use case to use case better, but it doesn't seem that we can't forecast the barrier at this given point. There will be a barrier, but we actually don't see it.
Okay, yeah, and in terms of the company's roadmap, clearly you've launched something exciting very recently, so perhaps it's a bit unreasonable of me to expect you to be doing other things, but if you like, is the main focus going to be on developing this solution more and working with partners, etc., and or do you also have sort of other ideas up your sleeve, should we say? And I'm sure you might not want to share those necessarily, but just whatever you can share as to the roadmap, as to what's going to keep you busy over the next couple of years, I suppose.
I mean, you very well anticipated it. So we're at the beginning of this paradigm shift. Currently, we're fully concentrating on Lena and the improvements of this architecture. I mean, traction comes when you solve real world problems, nothing else. And this is where we're currently up to. On the hardware side, we want to continuously bring updates to the market every year, at least one or two. And since the main performance driver, as I explained, of this technology is to rethink what's possible, we also extensively focus on developing mapping algorithms and software implementations. And as a startup, there is not much more space to consider other solutions based on the fundamental technology. There might be some ideas coming across the way when we emerge as a company, but currently we solely focus on Lena.
Okay, and maybe just in finishing, just sort of broaden out the conversation in terms of the impact of whether you call it photonic computing, optical computing, We've got the traditional server manufacturers, we've got the folks like Nvidia with the GPUs, and then companies like yourself in the phone. Just your thoughts as to how you think that ecosystem. You hinted perhaps that when you mentioned about co-processors, maybe some of these can coexist together, but just your thoughts, I guess, as to what impact you think photonic computing, optical computing might have over time. Clearly it's starting at that sort of high performance level, but how far down might it come to meet traditional servers, etc. And finally, sorry, it's going on a bit, but in terms of disrupting the market, we all know the traditional server manufacturers. Can you see a time when they will either be buying up companies like yourself in order to survive, or they'll just go to the wall as other? I know that sounds comical, but we're all aware of big names we thought would never disappear have disappeared. So your thoughts on the landscape, I suppose, is the simple question.
So, I mean, we have to increase the performance of a computer. A computer is a tool that helps us to calculate things, but that easy, right? And in order to reach this, I see that photonics at itself has to become an integral part of this landscape. So before I'm coming to the processor level, photonics in my eyes has to become also part of the transfer systems, the data transfer systems, may it be the transceiver structures within a card or from server to server, because we need to increase the transmission, the throughput basically of data in such a server rack system. And I'm not seeing that the currently used copper lines can cope with the necessity which we have basically to push these lines to. So that's going to be the first step of photonics into the data center world. Now and I'm expecting, by the way, that this is happening very soon. So by 28, I'm assuming that we see HPCs that regularly are going to deploy photonic interfaces in order to increase their bandwidth in the intra-communication. Now, from the photonics compute, I'm expecting that by the end of this decade, photonic compute systems like our NPU become a standard co-processing tool in all relevant HPCs that are focusing on AI. And this is because that these systems can much more energy efficient and faster execute on these, as I explained it several times, on these mathematical complex functions as they are needed for AI. But this doesn't mean that we are replacing all GPUs. There are spaces where we're going to need GPUs, especially when it comes to higher precision. We're going to need them. We need the CPUs to shuffle the jobs. We need the TPUs. This is what I mean. What we need to accept is that there are not one or two processors. We need to diversify the chiplet ecosystem, with one part going to be covered by our NPUs, and understand the whole system as one big computer that's going to increase the performance. This last question, what you said, it's always hard to anticipate which company goes big or small, or is disappearing or popping up. The only thing what I see is that the dynamic of how you have to change your narratives is accelerating extremely. So while when you look for, I think, 30 to 35 years, the CPU was the standard horse, so to say, in this ecosystem, which then out of a sudden was partially occupied from the GPUs. Then the TPUs came, now the NPUs are coming, the QPUs are developed. Companies who believe that an existing ecosystem is going to last for 20 years, they're probably already dying.
Okay, no, that's fantastic. I mean, it's been great to chat, and some brilliant insights into what's obviously going on at Quant itself, and towards the end there, the market more generally. So, Michael, really appreciate the time you give me. Thank you very much.
Thanks. It was great.